In the last lecture, we discussed the variation of small g, that is acceleration due to gravity, when we go out into space or when we go deep into the earth. We also discussed the gravitational potential and gravitational potential energy. We shall start again with gravitational potential and derive the expression for the escape speed. I shall explain all these things as we go along. The potential energy we already calculated for a unit mass, which is u equal to minus g m by r. This is at the surface of the earth, and r, let me remind you, is the radius of the earth. Now, suppose we go to a short height h from the surface, then what happens? Then we can write the gravitational energy u is equal to minus g m by r. You see, m is the mass of the particle, by r. R, small r, is capital R plus h. So, r plus h. We can take capital R outside, r into 1 plus h by r, and this becomes minus g m by r into 1 minus h by r, using binomial theorem and using the fact that h is small compared with the radius of the earth. So, therefore, we can write finally the gravitational potential energy of a mass m at a distance h from the surface of the earth as minus g m by r plus g m by r squared into h. We recognize that the first term on the right as the potential energy of m at the earth's surface, this minus g m by r we have learnt already, is the potential energy of the mass m at the surface of the earth, and this extra term is g h, m g h, because of m, and this g m by r squared is g. Therefore, the extra term is m g h. Thus, the difference in the potential energy of the body as it goes to a height h from the surface of the earth is delta u equal to m g h. That means, effectively we have put the gravitational potential energy of the mass to be 0 at the surface of the earth. Remember that since it is the potential difference or the difference in the potential energy that matters, we can take the 0 of energy at any place we find convenient. So, we can fix the 0 of potential energy at the surface of the earth. Then we can call the potential energy of a particle at a height h as u equal to m g h. That is, if I take a particle to a height h from the surface of the earth, then it gains in energy, which is m g h. When the particle falls back, it gives up its potential energy in the form of kinetic or other energies. We also recall that gravitational force is a central force. It is also a conservative force. So, if we go from A to B covering a height h, then the gain in potential energy is simply m g h, does not depend upon the path taken. And if a particle falls from B to A, then its potential energy decreases by m g h, no matter what path it follows. Now, since the energy of the mass m was 0 at infinity, in the process of falling to a position r in the gravitational field, an energy equal to the magnitude to its potential energy r is released. You see, since the potential energy is g m by r, when it falls from infinity, this energy is released. We have already seen this in the earlier lecture, that when a particle falls in the gravitational field, it loses potential energy, but gains other forms of energy, including the energy that it releases. Now, for a body bound to another massive body, such as the planet bound to the sun, the total energy must obviously be negative. Why is it negative? So that we need to do work to remove this body free of the gravitational potential. So, E is equal to half m v squared, that is kinetic energy, plus potential energy minus g m by r, and the sum of these two must be less than 0 for the particle to be bound. For example, for the earth to be bound to the sun, the total energy must be negative. So, that energy is required to be given to the earth to remove it from the clutches of the sun. Now, since the gravitational field of the earth or sun or of whatever body you consider is there and it always attracts particles towards it, is there a way in which we can make a particle free, so that it goes out of the gravitational field, say of the earth? Let us see whether it is possible or not. You know that if you throw a ball up, it always comes back. You throw and it comes back. You throw with a higher speed, it again comes back. If you throw with a still higher speed, it might go into an orbit around the earth, but it will be still bound to the earth. This orbit is within the gravitational field of the earth. So, how can we release the body from the gravitational field? We will see that we have to give minimum speed to the particle, so that it escapes the gravitational field, and this minimum speed required by a body to escape the gravitational field of the earth is called the escape speed. In fact, why of the earth? From any other surface, say a particle can have escape velocity from the moon or from say another planet. So, whenever the minimum speed required by a body to escape the gravitational field of another body is called the escape speed. It is obvious that the escape speed from the earth would depend upon the mass and radius of the earth, because the strength of the field is dependent on the mass of the earth and the radius of the earth. Therefore, the escape speed would also depend upon this. So, let us write the energy of a particle on the surface of the earth. It has kinetic energy half m v squared, it has potential energy minus g m m by r. Therefore, this is the total energy, and we have seen that this is generally negative for the particle to be bound to the earth. As the body gets away from the earth, its speed decreases. Why? Because remember I told you that the acceleration due to gravity is always vertically downwards. So, if the body is going up, the force is acting vertically downwards, and therefore, it will reduce the speed of the particle. So, as the body gets away from the earth, its speed decreases because of the pullback by earth's gravity. If speed of the body becomes 0 before it escapes the gravitational field, it will be pulled back by the field. You see, if it becomes 0 here, it will come back as we do that. If we throw a ball, it goes to a certain height where its speed becomes 0 and then falls back. This happens. So, if at a finite distance from the earth where the gravitational field is still active, if the speed becomes 0, the particle will be pulled back. However, if the speed of the body becomes 0 just when it escaped the field, it will not be pulled back. Suppose this is the boundary of the earth's field, beyond which the earth field does not act. If a particle reaches here, it will not be attracted back. If a particle is here, it will be attracted back. So, we are supposing that just at infinity, the velocity of the particle becomes 0, and it is not pulled back by the earth. So, the total energy of the particle is 0 just at infinity. Its kinetic energy has become 0 because V is 0, its potential energy has become 0 because R in the denominator at infinity becomes 0. So, therefore, the total energy of the particle at infinity has become 0. Now, the particle and the earth, they constitute a two body system, which is under the mutual force of gravitation, and therefore, the energy of this system must be conserved. The energy of the earth does not change much, because earth is a huge system, which means that the energy of the particle must be conserved. If it is 0 at infinity, it must be 0 at the surface of the earth. And what is the total energy at the surface of the earth? Half m v squared minus g m m by r, and this must be equal to 0. This gives us V equal to V escape equal to 2 g m by r, and plugging in the values of g, m and r, we can calculate that V escape is 11.2 kilometers per second. It is a huge velocity, but you see it depends upon the mass of the earth or any other planet and the radius of the earth or that planet. I am showing you again by this animation. Particle comes back with a still higher speed, it comes back with a still higher speed, it comes back, because velocity of these particles is less than the velocity of escape. However, when the velocity is beyond the velocity of escape, then the particle escapes. For velocities less than the velocity of escape, it comes back. For velocity greater than the velocity of escape, it escapes, and the velocity of escape is 11.2 kilometers per second. It is remember that artificial satellites are launched with speeds considerably smaller than this speed. Why? We do not want them to escape the gravitational field of the earth. We want them to be bound to the earth and revolve around the earth. There is generally a misconception that when a body is launched with the escape speed, the gravitational field of the earth ceases to act. This is not so. The gravitational field of the earth acts at each point of the path of the escaping body, because it decreases the speed of the particle. However, the speed becomes 0 only at infinity. At that point, there is no gravitational field to pull the body back, and the body escapes. I will give you the escape speed on 3 different bodies: Moon, Mercury and Venus. You can calculate, in fact, knowing the mass of these bodies, knowing the radii of these bodies, one can easily calculate the root of 2 gm by r, and these are the speeds. And look at this table again. You see that these are very small, 2.37, 4.25 compared with, let us say, Venus 10.39 kilometers per second, or of Earth 11.2 kilometers per second. So, what is the effect? The effect is that many particles that we find in the atmosphere of the earth, they have velocities on these Moon and Mercury higher than the escape speeds, and therefore, they escape. Field of these gravitational field of Moon and Mercury is weak. The particle velocities are higher than the escape speed, therefore, they escape, which means that Moon and Mercury have no atmosphere, unlike the earth or unlike Venus. They have no atmosphere. Even on the earth, this effect is felt. Many of the light gases like hydrogen and helium are highly deficient on the earth, although they are most abundant in the universe. On the earth, they are deficient, because these are light gases. Their thermal velocities are very large, and sometimes they are larger than the escape speed from the earth, and therefore, they escape. So, during the formation of the earth, many of these gases, much of these gases, helium and hydrogen, they just escape the earth, and so the earth is deficient in these gases. Let us take an interesting case. Suppose the escape speed is equal to the speed of light. That means that the is equal to the speed of light. That means light also can escape. That means if the light escapes, what happens? There is no light from that object, and therefore, the object becomes invisible. Such an object is called a black hole. You see what is happening? We are saying that the escape speed is equal to the speed of light. That means light, the all other things can escape, but light cannot escape. That means light is bound to that object, cannot be seen from outside, and therefore, this object becomes black, and it is called black hole. So, let us calculate this speed for the sun. Suppose sun becomes a black hole someday, what would be the radius of the sun? We are assuming that the escape speed from the sun would be the speed of light. So, we just plug in the numbers, and we can find that the radius of the sun, if it becomes a black hole, is only 3 kilometers. 3 kilometers is a very short distance, but that is the radius of the sun if it ever becomes a black hole. I can assure you that the sun will never become a black hole. This is just a theoretical imaginary calculation. Sun will never become a black hole. But what happens to the, suppose sun becomes a black hole, what happens to the orbit of the earth and other planets? Remember, we saw that the whole mass of the sun or earth or other planets can be supposed to be concentrated at the center of these objects for the other objects to be revolving around them. So, whether this mass is concentrated in 3 kilometer radius or the actual radius of the sun does not matter. What matters is the mass of the sun being felt at the center of mass of the sun. And if this is not disturbed, the planets will keep on going around the sun in their present orbits. Artificial satellites. I have already pointed out that satellites are launched with velocities much less than the escape velocity. Why? Because we want to keep them in the Earth's field, we do not want them to escape, and they are usually launched from a height of about 300 kilometers. So, that the resistance of the air is small and therefore, not much energy is lost in overcoming this drag due to air, and they are launched with velocities of the order of 8 kilometers per second. So, that they can orbit the earth. Remember that artificial satellites also work under the effect of gravitational field. Therefore, whether they are artificial satellites or whether they are natural satellites like the moon, they obey Kepler's law, which is T square by r cubed constant. T is the time period and r is the mean distance from, say, for a planet from the sun, or for an artificial satellite from the center of the earth. So, T square by r cubed is constant. T is the period of the artificial satellite and r is the distance from the center of the earth of this satellite. And we can use this T square by r cubed as we use for other planets. For example, that plugging in the values, we can find that the satellites which revolve with a time period of 1 day, which are used for communication, etc., these planets, their distance is from the center of the earth, it is 6.6 earth radii. From the surface of the earth, it is 5.6 earth radii, which is roughly 36,000 kilometers. So, these geostationary satellites, they are at a height of about 36,000 kilometers from the surface of the earth, or it is 5.6 earth radii from the center of the earth. The planets, the satellites which are at lower altitudes, they are only a few hundred kilometers away, say up to 1,000 kilometers away, and they move fast. Their time period is of the order of hours. You can calculate again using T square by r cubed, that their time period is of the order of hours, say 60 minutes, 70 minutes, 80 minutes, like that. In the next lecture, we intend to take the things like surface tension, the properties of fluids.